Okay, this is the second hour of Physics 1A, 1C for November 8th, and now we're talking about Ampere's law. Okay, so let's see if I can motivate why we would care about something about like this. So, when we were doing static electricity, we learned about Gauss's law, right? And we found that Gauss's law told us that if you want to find the surface integral of E dot dA over a closed surface, there's technically supposed to be two lines here, it's a surface integral, so we write an S down there. We found that the amount of charge that was enclosed inside of the surface divided by epsilon naught was equal to that quantity right there. We then said, suppose that we do the same thing, but we replace the electric field with a magnetic field, and we found out that when we did that, because there are no magnetic monopoles, you get zero. All right. Now, we also talked about something called electric potential. And for electric potential, we also do an integral. But with this integral, we found that if I take the integral of E dot ds, that this produces what we call EMF, or delta V, however you want to call it, right? This produces EMF. So the question in regards to Ampere's law is, what do you get if I do the integral of B dot dl? In particular, what do we get if we do it over a closed path? So the reason why we might care about this is because when we looked at Gauss's law, when we did a surface integral with the electric field, we got Q over epsilon naught. You did the same thing for the magnetic field. We got this result that you always get zero. So the question is, when you do E dot ds, you get this thing called EMF. What do you get when you do B dot ds? Well, to keep it consistent here, we'll call this one also ds. Although your book likes to use dl. They mean the same thing though. It's just an arc length, right? Okay. So Ampere's law is about this. What is this equal to, right? So we're going to start off by doing this for a very simple arrangement, and then we will use the result we get and kind of prove that it's going to be the same result for all systems. So here's our system. We have a current carrying wire, I. It carries a current coming out of the screen like this. And what we're going to do is we're going to say around that, there's going to be a circular magnetic field that looks like this. And the magnetic field vectors are going to point like this, around in a circle like that. And what we're going to do is we're going to calculate the integral of B dot ds along this loop. So our ds's are going to be lines like this, lines like this. ds is always going to be parallel to the circle, tangent to the circle, and parallel to the magnetic field. So we know at this location, for example, that the magnetic field also points in the same direction. And you can see that ds and b point in the same direction as long as we go around this loop in a clockwise fashion. So if we ask the question, what is the integral of b dot ds equal to? What we can note is that we know that the angle between b and ds is always zero. So we can rewrite this as just the integral of b ds. Then we can say, but if this is a long current carrying wire I that carries current out of the screen like this, we know what the value of the magnetic field for that system is. It's mu naught times I divided by 2 pi multiplied by the radius of the loop. So in this case, if the radius of the loop is r, then this is the value of b. We can pull that into our equation here and say now we're doing the integral of mu naught I over 2 pi r ds. But what we can say is that all of these quantities here are constant with respect to s, meaning that it's a symmetrical system. It doesn't matter if I'm here or if I'm over here. the value of B is always the same. So all of those terms can be pulled out of the equation. So we just get mu naught I over 2 pi times the radius of the loop, and then we just need to do the integral of ds over the entire circular path right here. If we do that, similar to the problem we did just a second ago, we're going to get 2 pi times r. I'm sorry, yeah, 2 pi r, yep. Which is then remarkably actually going to cancel out. The radius of the loop is gone now, and we find that the integral of b dot ds around a closed loop is equal to mu naught multiplied by the current. And this is basically Ampere's law. Ampere's law states the following. Ampere's law says that when you calculate the integral of b dot ds, you always get mu naught times the current that flows through any surface bounded by your path. So I'll just write it like this. It's the integral of b dot ds is equal to mu naught times I enclosed, and I enclosed is the current. How do we call it? So it's the current that passes through any surface bounded by your path. The current enclosed is the current that passes through any surface bounded by the path. And with that definition, this is Ampere's law. This is one of Maxwell's equations. In fact, this is the third. This is number 1. This is number 2. This is number 3. This one will be part of the last one, but we need to learn about another way you can produce EMFs called Faraday's law. That'll be number 4. So we'll just go ahead and say this is number 4, but it's not complete quite yet. Those are the 4 Maxwell equations. So Ampere's law is the newest one we've learned about, and it says that when we take this integral of b dot ds, you get mu naught multiplied by the current that's enclosed by this, and I enclosed is the current that passes through any surface bounded by the path. So it's this type of the fact that the I enclosed shows up here is very reminiscent of the fact that in Gauss's law you have Q enclosed. There's a lot of similarities there. I'll just give you some examples of how this might manifest itself. So suppose in a region of space I tell you that I have an area where I have current of 5 amps coming out right here. I have a current of 7 amps going into the page right here. And we'll do a couple more. Let's say we have a current of 1 amp coming out of the page here. And then right here, let's say we have a current of 3 amps going into the page. And then around these, suppose that we want to have some path along which we're going to calculate b dot ds, okay? And let's say that one of my paths goes like this. We'll call that it's like path 1 or surface 1. I'm going to call it S1 for surface 1. Let's say that another one goes around like this. Let's use different colors. You know what? Let's do it one at a time. You all tell me, if I call this path right here my path 1, how much current is enclosed by that path? How much current passes through any surface that's bounded by the path? It should be 6 amps, because there's 5 amps plus 1 amp for a total of 6 amps. And to understand what I mean by a surface bounded by the path, this is the surface bounded by the path here, right? That's what we mean by that. Creates a plane, which is a type of surface, right? Okay, let's try another path. Here, let's just do color coding to indicate the difference between each of these. So then if I draw a blue path, let's say, and I draw it around all of these ones. Okay, and let's keep going counterclockwise. I'll talk about what happens when you switch directions. So let's say we go this way. What is the current enclosed by that path? Here, if a current goes in, it's going to be negative. If it comes out, it will be positive. Okay? How much current is enclosed by that path? -9 amps. -9 amps, that's right. Because you take 7 plus 3 is 10, but they're both in, so that's -10 plus 1 is -9, right? Let's do another one in yellow. What about this one? Again, we're going to continue to go counterclockwise. What about the yellow path? What's I enclosed there? We got 5 coming out. We've got 3 going in. 5 minus 2 is, or 5 minus 3 is 2. Positive 2. Pretty easy, right? Pretty easy. Pretty easy. So what happens when we go in the opposite direction? Well, if we go in the opposite direction, you get a negative sign, okay? So if I have a situation where let's just do one current to keep this simple. Suppose I have a current that's coming this way. Here we can write down here, right? Let's say I have a current I that comes this way. And now normally the path would go clockwise, but suppose that I surround this with a circular path that goes counterclockwise. So suppose I do a path that is counterclockwise. So what is that going to be? This way, right? So say this is the direction of my path, right? And the direction of the magnetic field is the other direction, right? If my path goes like this, and I want to find out what the enclosed current is, I guess you can think about it 2 different ways. So I don't want to kind of force you down a certain line. So if the magnetic field goes this way, but my path vectors point opposite to it, right? If S is this way, then I believe what happens is that when we do B dot ds, in this case, it's going to be equal to negative BDS. Okay? But the current that's enclosed, in this case, is going to be negative I. Because now if my path goes this way, my current comes out, the current enclosed is negative I. So what happens is that when I do the integral of B dot ds is equal to mu naught I enclosed, you end up getting a negative sign on this side, and you get a negative sign on this side, and they kind of cancel out with each other, which means you get the same answer, effectively. I didn't even tell you what we use Ampere's law for, but we actually use Ampere's law to calculate B, as you're going to see in the upcoming examples that we're going to do. Okay. So this diagram here is designed to talk about what I just mentioned. Let's expand this out until it doesn't look all squished anymore. Okay, that looks better. Let's make it a little bigger, and let's look at what they say. 3 different integration paths for the line integral of B in the vicinity of a long straight conductor carrying a current I out of the page, as indicated. The integration path is a circle centered on the conductor. The integration goes around the circle counterclockwise. The result is the integral of B dot dl is mu naught times I. Same direction, right? Part B, the same integration path as A, but the integration goes around in a circle clockwise. So here, similar to what I was drawing here, you see B goes this way, dl goes this way, and now the integral of B dot dl is going to be negative mu naught I. Did I confuse you here? Maybe what I should do is do what they do and just be consistent here and just say this is negative mu naught I. And then you get what you get over here. Now there's a third possibility. This is the problem we're going to do in a second, where we include a path, right, where this picture is so hard to see. I'm going to blow this up a lot bigger so you can really see what's going on here. All right, so here's our current, right? And now our path is this, I don't know, this shape right here. So it goes from A to B to C to D and then back to A again, right? What happens here is that this path does not enclose any current. Can you all see that? No current passes through the path or surface bounded by the path. Let's look at the two edges. Along the edge D to A, the direction of the magnetic field is perpendicular to the path. So the contribution to B dot dl here is 0. Along this path here, right, B is also perpendicular to the path, so you get no contribution here. The only place we're going to get contribution is from the line A to B, and then from the line C to D. You'll notice that along the line A to B, B and dl point in the same direction, so B dot dl will be positive, but along this one, B dot dl point in opposite directions, so B dot dl will be negative. And what you'll find is if you do the calculation that B dot dl along AB is exactly equal and opposite to B dot dl along C to D, which is why you get that the integral of B dot dl is 0. And I would definitely encourage that you try to work that out for yourself. All right, so, the other thing that happens here is that the size of B here is smaller than the size of B on the inner ring here, but the path length is longer, A to B, than from C to D, so that's how you get the exact cancellation going on here. Okay, now I'll just write down what I said earlier, which is that we are going to use Ampere's law to solve for B. Similar to the way that we used Gauss's law in the past to find the electric fields. So here is an example where we can do that. Okay. The field of a solenoid. So a solenoid, there's a lot of words here. There are a lot of words here. A solenoid consists of a helical winding of wire on a cylinder, usually in a circular cross-section. Let's just stop right there so we can understand what a solenoid is. You're going to see that word show up a bunch. Suppose that I take a piece of cardboard, for example, okay? I take a cardboard tube, like the inside of a paper towel holder, for example, right? And then I take a wire, right? And I take my wire and I run it across the top here, and then I just keep winding it, the same piece of wire. It goes back here, and it comes back here, and it goes behind, and then it comes back out this side, and so on and so forth. So this is what a solenoid is. You basically just take one piece of wire, you run it around some kind of core, and you've now produced what we call a solenoid. Solenoids show up all over the place in this class, but they also show up in things like in your car. I believe the starter in your car has a solenoid that sometimes has to be replaced. But this is what we call a solenoid. I know that I'm writing in a place where you can't see, but I'll scroll down a little bit. That is what we call a solenoid. Wire wrapped around something, that's a solenoid. It doesn't have to have current flowing through it for it to be a solenoid, which means the word solenoid just refers to a wire that has been wrapped around some kind of something to hold the wire, basically. So when I say solenoid, that's what you should think. Coils. Coils of wire being wrapped around some type of something. All right, so a solenoid consists of helical winding. So helical just means wrapped like a helix on a cylinder, usually in a circular cross-section. It doesn't have to be circular. This could be a square. It could be a triangle. It would still be a solenoid. Usually they'll be circles. There could be thousands of closely spaced turns, often in several layers. So you could have multiple layers of these wires. You just keep wrapping wire over on top of itself. Each of which can be regarded as a circular loop. For simplicity, figure 28.22. Oh, what is that one? Well, it's basically my picture, so nothing special. It's basically this. this figure shows a solenoid with only a few turns. All the turns carry the same current I. Okay, so now we have a current I flowing in here, and we'll have a current I coming out this way. Yikes, I look at their picture. I want this to be the same. That's the same. This is good. This works. Okay, current I flows in here. That means the current is going to be flowing kind of upwards here, and so on and so forth throughout all the pieces. The current's always flowing this way. On the backside, so the current basically curls around like this. All right. All the turns carry the same current I. The total magnetic field at every point is the vector sum of the fields caused by the individual turns. We saw earlier that we know how to find the electric field of a ring. So if you vector sum all those fields, the figure shows field lines in the x, y, and xz planes. You know what? This is stupid. We're going to show you. I'm going to get the picture from the book because they're obviously referring to it, and I guess I left it out, and I don't want to confuse you all. So let's pull the picture from the book up. I'll copy paste it in here. All right, we're on chapter 28. Magnetic field, applications of Ampere's law. Here's their picture. And all of its beautiful color with all the artifacts and stuff. We're gonna do paint, paste, select, and then back to here. All right, now we actually have the picture they're talking about. I forgot that that we needed this. Okay, so let's go back. All turns carry the same current I. So here's our solenoid. We're just seeing like a quarter section of it here, right? Drawn in blue are the magnetic field lines created by the solenoid. The solenoid tends to produce a magnetic field similar to a dipole magnet, actually. The figure shows the field lines in the x, y, and xz planes, right? So there's the xy plane and there's the positive xz plane. We draw field lines that are uniformly spaced at the center of the solenoid. Are they uniformly placed? I guess they are. The field lines in the center here, they're pretty uniformly spaced. Exact calculations show that for a long, closely wound solenoid, half of these field lines emerge from the ends and half leak out through the windings between the center and the end, as the figure suggests. If the solenoid is long in comparison with its cross-sectional diameter, so if it's really long and skinny, and the coils are tightly wound, the field inside the solenoid, near its midpoint, is very nearly uniform over the cross-section and parallel to the axis. The external field near the midpoint is very small. Use Ampere's law to find the field at or near the center of such a solenoid if it has n turns per unit length and carries a current I. So basically what they're telling us is this. Inside of the solenoid, our magnetic field lines are going to be roughly uniform, and they're going to look something like this. The field lines inside are going to look something like this. Okay? Those are our magnetic field lines. And our goal is to use Ampere's law to find the field at or near the center of such a solenoid. So we want to know, kind of in the middle right here, what's the size of the magnetic field? And in order to do that, we are going to look at a cross-section of our solenoid that looks something like this. So imagine that we come through with a knife. So imagine we have a knife right here of some kind. So we have a knife, and we just cut our solenoid in this direction. And we look at a cross-section in that direction right there. I don't know why I felt like drawing a knife there. That seems kind of silly. Okay, so if we do that, then our solenoid, at least in the center, so if we basically take a piece of this, like right here, and we just cut that right there out, it's going to look something like this here, where on the top, the current is going in. That's what these X's represent here. On the bottom, the current is coming out. That's what these dots represent here. And you can see that on our picture because if you look at the direction the current's flowing, the current should be coming out on this side, right? So dots, and it should be flowing in on the top, like that. And so that's where that comes from. And what we're going to do is we're going to use Ampere's law. We're going to do B dot dl is equal to mu naught times I enclosed. And our integration path is going to be this box right here. We're going to integrate along A to B, and then B to C, and then D to A. These little squiggly lines right here mean that when we carry out this integration path, we're going to be running basically our integration path is going to start inside of here, but it's going to go really far away and then continue back like this. That's what those squiggly lines represent, is that our integration path is going to be very long. All right, so we need to do this along all four sides. The first thing we notice is for our integration path, here, let me be consistent and stop writing DL, even though that's the way the book writes it. Let me keep writing my own way, B dot ds. So inside of here, ds is going to point this way. On this side, ds will point this way. On the top, ds goes this way. And on this side, ds comes down this way. But we're going to make the assumption that the size of the magnetic field in this region up here at the top is really small. So that means that when we do our integral, we're going to break it up into four different parts. There's going to be the integral of B dot ds from A to B. There's going to be the integral of B dot ds from B to C. The integral of B dot ds from C to D on the top right there, plus the integral of B dot ds from D to A. And that will complete our this, right? All right, so first things first. For this one, we notice that the direction of the magnetic field and ds are parallel to each other here. And that means that we can write this as just the integral of bds. And we're going to be able to pull the b out of this as well. So now we're just going to have the integral from a to b of ds for this one, plus. From b to c here, the magnetic field points to the left, right? So there's a right angle between ds and b. So this term is going to be 0. On this piece right here, the b itself, when we go from c to d, we're saying that b is equal to 0 out here. Only approximately true, but good enough for this class. So this is also going to be 0. And the integral from d to a, along this path right here, is also going to be 0. Now, one thing you could really say that would be even more accurate is, suppose we look at this picture down here, where we have the three-dimensional picture, right? And imagine now that we do that same thing. So here's our path. We go this way, and then we go straight up in the y direction. Straight up in the y direction here. And then we continue back this way, and then we come back down here. I just want to talk about this path and this path here. Now, in this picture, where you can see the actual field lines, or if you look at the front cover of your Physics 1C lab manual, there's a picture of a solenoid there as well with magnetic field lines drawn. At the very least, even if b dot ds isn't 0 along this path and 0 along this path, because as you can see, there's these lines that are kind of curving, so there could technically be some b dot ds that you would get here when you do the integral. Whatever you get, this side is going to be positive, and this side is going to be negative, or vice versa. So if along this path you get something like positive 9, on the path back this way where it's perfectly symmetrical, you're going to get negative 9. So what I would say that's more accurate is that this is going to cancel out with this. One will be positive and one will be negative. Then the final part about it that's maybe a little bit confusing is why is b equal to 0 here? And the reason for that is because instead of going along a line like this, we're actually, again, going all the way out here and down here. And so the idea is that up here, b is not exactly equal to 0, but it's probably approximately equal to 0. So that's how we get those zeros there. All right. And we know that when we calculate this, this should be equal to mu naught multiplied by the current enclosed. On our left-hand side now, when we do the integral from a to b of ds, that's basically just going to be the length of the line from here from A to B, which in our case is defined as L. So the left-hand side of this just becomes B times L. And we're multiplying that times mu naught multiplied by the current enclosed. So as we said before, the current enclosed is going to be equal to the amount of current that actually flows through the surface bounded by our path. So that surface in this case is this surface here. And we've said that it carries current I, right? So for every one of these x's that we have right here, that is another current that's equal to I that's passing through our integration path, right? So how many do we have right there? How many i's? There's one I, 2, 3, 4, 5, 6, 7, 8. Looks like 8, right? So I think that our I enclosed is going to be 8 times I. We're almost done. Anyone have any questions about that? Does that make sense to everyone? Any questions? Okay, so let's rearrange this a little bit here. So I'm going to rewrite it as B is equal to mu naught times 8 divided by the length times I. And now what I'm going to say is that 8 over L is the number of turns in this region, right? But what we were told in the problem is that our solenoid has n turns per unit length, right? So what I'm going to say is that 8 over L could also be written as B is equal to mu naught times the number of turns for that unit length times I, which means that B is equal to, if we say that little n is equal to the number of turns per unit length, then the magnetic field is going to be mu naught times little n times I. Again, somewhat complicated derivation, but very simple result. Mu naught multiplied by the number of turns per unit length and then multiplied by the current. This is going to be the magnetic fields at the center of a solenoid. You're going to need to know this because it's going to show up not just in this chapter, but in every chapter we do from here on out. We will be using solenoids quite frequently. Solenoids are the magnetic equivalent of a capacitor, only in the sense that they are going to produce our straight magnetic field lines that we're going to need for solving certain types of problems. That is not to imply at all that a solenoid is like a capacitor in any other way, although it can store energy in its magnetic fields the same way that a capacitor can store energy in its electric fields. So they do have quite a few similarities, but anyway, so there we go. You take mu naught, you multiply by n, and you multiply by I. This tells you that you can make a bigger magnetic field by increasing the number of turns per unit length, which means that the biggest magnetic field you're going to get is when you wrap a whole bunch of wires very tightly in one region, and maybe even just keep wrapping the wires over and over and over and over again on the same object. A solenoid, another word for a solenoid, is just an electromagnet. This is very similar to what an electromagnet is, right? And the field of a solenoid is very similar to the field of a dipole or magnet. All right, so that's one way we can use Ampere's law. Another application of Ampere's law is here. the field of a long cylindrical conductor. At least one or two of your homework problems from the lab manual. That's right. That's right, Mr. User Account. That is correct. Okay. The next thing we want to do is to look at the field of a long cylindrical conductor. And now what we're going to want to do, we've already found the magnetic field of a long cylindrical conductor, like a long wire, outside of the wire. We'd now like to find the magnetic fields on the inside of the wire. Okay? So again, we're going to use Ampere's law to do this. Oh, I'm sorry. So let's get to it. On the outside, we have B going around here. Let's look at our picture. So the gold thing here is our wire. It has a current that flows in this direction here, from the right side of the picture to the left side. And we've drawn what we call an Amperian loop. You know, we had Gaussian surfaces. We now have Amperian loops. And along our Amperian loop, we're going to indicate that our ds vectors are going to point parallel to the direction of the magnetic fields. So that's the direction of our ds vectors are going to be. And then we're just going to evaluate integral of b dot ds in the region where little r, is greater than big R, where big R is basically the radius here, and little r is going to be the radius of our loop. See here, r greater than r. So we're going to say integral of b dot ds then is equal to mu naught times the current enclosed. With a loop that goes outside of our cylinder, the current enclosed is just going to be I. And on the left-hand side, we have the integral of b dot ds. We can say b and ds are parallel to each other. The magnetic field all along that loop should be constant. So we can just say b times the integral of ds, which is going to be b multiplied by 2 pi times the radius of the loop, which is going to be equal to mu naught I. And here we've just basically rederived a result that we did in the last chapter. I think it's the same chapter, actually. So we're still in the same chapter. That is for r greater than r. That's the easy one. The trickier one is to do the region where r is less than big R. And that's the Amperian loop that's been drawn inside of here. We're again going to take our direction of ds to be the same direction as the magnetic field at every point to keep things simple. And now we're going to say integral b dot ds is equal to mu naught times the current enclosed. The tricky thing now is to find the current enclosed. The left-hand side of the equation is still going to reduce down to b times 2 pi r, but we now have to find out what is the current enclosed. Now, the current enclosed by our loop is no longer going to be the total current flowing through the wire, right? It's going to be some fraction of the current that's flowing through that wire, right? And we can say that it's just going to be the amount of current that's contained in here. Now, if we look at the problem, it says the current is uniformly distributed over the cross-sectional area. That doesn't always have to be the case, but it is in this case. Since it's uniformly distributed over the cross-sectional area of the conductor, what we can say is that the current enclosed should be equal to the ratio of the areas times the total current. That is to say, it should be pi times r squared divided by pi times big R squared multiplied by the total current here. So if we plug that into our equation here, we're going to have b times 2 pi r is equal to mu naught multiplied by the current enclosed, which is going to be little r squared divided by big R squared multiplied by I. Rearranging, we get that b is equal to mu naught times I divided by 2 pi times big R squared. Then we have to multiply by the only variable in this case, which is going to be r. And this is going to be the region where little r is less than big R. So we could even plot what this looks like here. If we plot the magnetic field as a function of the radius. Sorry, this should be magnetic field up here on the y-axis. And this should be the radius here. The distance away. Then we find that in the region where r is less than r, so let's say this is big R right here, the magnetic field grows linearly. In the region where r is greater than r, it falls off exponentially. Or as 1 over r. That's not exponential, just as 1 over r. And there we go. Any questions? I will say there is a more general way to do this, and your homework won't be quite this simple. For you, if you want to find the current enclosed, what you're going to need to do is you're going to need to do a double integral of J dot dA, where J is current density. And in the problems, I'll give you an example of how this could come up in a problem that you're going to do. So for example, so the problem we did, the current was uniformly distributed, right? Actually, I'll just stop for a second. Any questions about what we did so far before I make it harder? What if they're equal? You mean what happens when r is equal to r? You can check for yourself, but both equations give the same answer when r is equal to big R. They match at the boundary. Is that what you mean? Yeah. Check it for yourself. Plug in little r equal to big R into both equations. You will get the exact same thing. In both cases, you will get mu naught I over 2 pi times big R. Any other questions, or do you all understand this? It's actually, I guess we've done so much stuff like this, I could believe that this seems relatively straightforward to you, but I know these ideas are new, so I'm sure for a lot of you, you're still a little lost, and that's okay. All this stuff makes a lot more sense when you actually go to apply it, when you do your homework, and then you start to understand it well, and hopefully you understand it well enough for taking an exam. And then, 2 or 3 years later, you're not going to really understand any of it, but that's okay. You can always reteach it to yourself once you've learned it once. Okay, so the current density, if you're given that your current density is not uniformly distributed, those words uniformly distributed are why I can use this. This is because there's a uniformly distributed allows me to do this. Okay, and it says over the cross-sectional area. That's why I can use a ratio of the areas here. But if you're given the fact that your current density, let's say, is equal to like k times r to the 4th, for example, where k is just some constant, then you have to use that equation to find what your current enclosed is. So the way that's going to work is your current enclosed is going to be equal to the double integral of JDA. Dot product will go away as long as your area vector points this way and your J points the same way. And now you need to figure out what dA is going to be equal to. So for dA, what you have to do is you have to say, suppose that I've got my cylindrical conductor here, and I am looking at an Amperian loop that looks something like this. Then my dA is going to be a thin ring with thickness dr that has a radius r, thickness of dr, which means that your dA will be the area of that little ring right there. And as you've seen before in this class, the area of that ring should be equal to 2 pi r dr. So when we're doing our current enclosed, we'll plug in our J, which is k times r to the 4, plug in our dA, which is 2 pi RdR, right? And now, to find our current enclosed, we need to do our integral, which actually becomes a single integral after we plug in that dA, which is now going to be k times 2 pi times r to the 5th dr, which will obviously be, and now you're going to need limits here too, right? So let's say your limits, like for example, are from 0 up to some point a or something like that. Let's say that let's say you're going out to some radius a or something like this. You go from 0 to a of this, so obviously you would get 2 pi k r to the 6th over 6th from 0 to a. Now I know for a fact that some of the problems that you have on your homework involve situations where you have a ring like this, where there's an inner ring A, an outer ring B, and then all of the current is coming out like this. So here's your current. And I think even in the pictures you'll see in your book, it's going to look something like this. In this case, when we're doing this, you're going to have to integrate. Like if you wanted to find the electric field out here, if you want to find the magnetic field out here, you would be integrating from A to B. And if you want to find the electric field in this region here, you'd have to integrate from A to R or something like that, right? Does this stuff look familiar to you? Does this look really familiar to what you were doing in like the Gauss's law problems and stuff like that, right? It's the same idea. It's exactly the same. So you should have a lot of, you thought chapter 1 was over. Yeah. Joke's on you. The good thing here is that this is really a repetition of all that difficult stuff we did at the beginning of the class. So since you've done it before, now when you go and you look at those problems, you already you've seen this kind of stuff show up before, right? And I'm just telling you that now this is your I enclosed. In fact, this allows me to write down a more general version of Ampere's law, which says the integral b dot ds can now be written as mu naught multiplied by the double integral of j dot dA. And this is actually a form that we're going to need later on when we rewrite Maxwell's equations. So this is actually the more general form of Ampere's law. Although, as we're going to find out here at the end of the next chapter, it's actually not complete. There's actually another term that we're missing here. But we'll leave that till later. Okay, can we take a break now? We can. We can take a break now. We are just going to have to skip all this stuff, unfortunately. Maybe we'll talk about it later. There's a section in your book that's on types of magnetism. So it talks about diamagnetism, paramagnetism, and ferromagnetism. Ferromagnetism being the one you're most used to. We got to skip some stuff. I'm going to leave that for you to learn on your own. If we were meeting in person, I would show... if you remind me, if you want to see the difference between paramagnetism, diamagnetism, and ferromagnetism, I have a good demo that I can show you. Just to summarize what those topics are about, there are things other than iron that are attracted or repelled by magnets. And one of them is water. Water actually has magnetic properties. You can actually show that water, I can't remember which one it is. Water is either repelled or attracted to a magnet. And off the top of my head, I don't remember which one it is. But I'll show you a demo of how that's the case next time if you remind me. There's so many demos I want to show you at this point. Hopefully we can get to some of them next time we're in lab. These labs are so hard, though. It's really hard. There's a bunch of wire demos I want to show you, yeah. It's really hard, though. Like the last lab we were doing, I mean, everybody was working the whole time, you know? There's just so little time to stop me like, hey, check this out. But if I really focus on it, we can do it. I'm just always worried that it'll slow you down. I think the next lab's kind of long, too. Regardless, we're taking a break, and we come back, we're actually going to start talking about Faraday's law of induction, so we'll move on to chapter 29. So we're going to break until... We'll do 3:30.